All right. First lesson in our third unit of the year. Congratulations, by the way, for making it. Man, I got distracted by the stories over March break that I didn't talk about our reflection, what we can do to reflect over the past 2 units. Anyways, where's my pad? All right, let's get started. Algebra. Algebra, and essentially is like I'm gonna say, it's a short way of saying we don't know a quantity. We have an equation, we have some mathematical statement, but it's always gonna have some unknown quantity. And for whatever reasons, we always label that unknown quantity in letters, not happy faces, not symbols like stars and exclamation marks, something like that. It's always some kind of alphabetical letter. In fact, if you get to grade 10 and grade 11, we start using Greek and Latin letters. So the Greek alphabet, yes, it might start with A for alpha, but alpha is typically written not as a letter A, but as like a little fish. We have beta, right? And instead of the letter C, we would have gamma, like the G letter. Like it's just a lot of different letters, right? And if you know like movies with fraternities and sororities, right? And if you go to like hashtag, like hashtag Twitter and Instagram, what do they call it? They call it like Greek life or whatever. And they're just like, oh, I'm so cool, whatever. It's not really cool, okay? But they always have like, I'm from like gamma, gamma, beta. Where are you? Like it's all from these Greek Latin letters, okay? Except we're talking about it mathematically. The letters in the world of algebra are called variables. Why? Because they can vary, right? The letter X could be a 1, it could be a 2, it could be a 3, it could be a number. And since it can vary, Elliot, write it down, it is a variable. Make sense? Okay. A term, here's another word. A term is an expression, so it is like a word, a mathematical word, formed by the product multiplication of numbers and or variables. Here's an example of a term. Have you seen that before? What number is that? 5. You've been working with terms before, but here's a difference. That is also a number, but now it involves a variable. This is what I mean. If X was a 1, what number is this? 5 times 1, that's a 5. If X was a 2, what number is that? 5 times 2 is 10. If X was a 3, what number is that? 5 times 3 is? Do you see how the result could vary depending on the X? That's why we call it a variable. It can vary. So don't be too scared of the actual word. It just means X is a number. We don't know what X is, so we just call it 5X for now. We'll figure out X later. Here we go. Here's another variable. You ready? Negative 5X squared. There's a term for you. This entire thing is one term. It is a product, a multiplication of a number and a variable. Now I'm going to talk about this number specifically later. I'm going to give it a special name because it's part of the terms, but bear with me. How about this? 2m. Again, another letter. Just because it's not X doesn't mean it's not a variable, right? How about negative 41xyz squared? Are they multiplying? Think about it in terms of BEDMAS, right? There's nothing in between these, so we can assume that they are multiplying with each other, just like here. 5 times x, negative 5 times x squared. So this entire thing is one variable. Now I'm going to get really stupid here. 11 over 29, A, B, C, D squared, E, F, G, H cubed, okay? It doesn't matter. It's one term. Beating a dead horse. Does everyone understand? Is everyone okay? So far, so good? All right. So let's break this down. If I have, let's say, -2 x to the power of 4, I'm going to divide this into two different sections. Let's use this blue. As you can see, a term will have two different parts to it. An entire term has some number multiplying product with the variable. So I'm going to call this number, give it a special name called coefficient. And the variable, well, you know what that is, that's a variable. Okay. But please note, the variable also includes the exponent. So a variable x and a variable x squared are different. They are not the same. And just as a little bonus, we're going to call the exponent, well, we call it an exponent. In algebra, we also call this a degree. So this variable is to the 4th degree. You can say that. It's just another way of describing things, that's all. I hope you feel okay with that. So up until now, it's not really math. It's just trying to figure out the terms. How is everyone doing with this? Thumbs up. Okay, sounds good. All right, let's get to it. Now, we're extending. I told you that this was a term. 5x is a term. -5x squared is a term. And because they're a term, you know that this is a number. It's some number. I just don't know what it is. This is some number if I knew what every single letter represented, right? We are going to a situation where we can have more than one number or more than one term adding or subtracting with each other. So moving down to the next bit, take a look. Here's a Greek Latin lesson for you. I have the word poly and the word nomial. Anyone have any idea what either of those two root words could mean in the Greek Latin language? You got one? Poly is many, like polygon. We talked about that. Really good. So this is many. Nomial? Want to take a guess? Yeah. Many numbers or many terms. So a polynomial is an algebraic expression with one or more terms. Many could be 2, many could be 3. I don't know. Check it out. 5x is called a monomial with the prefix mono because it has one term. 3x, -5, called binomials with the prefix bi because it has 2 terms. And of course, here's one term. +4x is another term. -1 is another term. It has 3 terms. Okay. Again, some of you are like, this is obvious. I get it. Other people are like, I didn't know what these words meant. Please fill in the chart below. Take a look, see if you can count how many terms there are, and therefore mention what the, I guess the name of the polynomial might be. Yes?
A term, does it have to have like a root number, or can it just be like x2? Would that be a term?
S squared?
x2.
S.
Like in the chart, for the second row, does the term have to be a number, or can it just be like the x2 would be considered a term?
Yes, x squared is still a number. So x squared is the same as 1x squared. We just don't write it. So the number is, a coefficient is still there. Okay, I'm going to pause the video and just give you a record. So a lot of people are on the right track. It's really, really good. By the time we get to 4 terms, it gets a little annoying. So instead, I will show you what we do. Number of terms, 1, monomial. Number of terms, 3, trinomial. Number of terms, 2, binomial. Number of terms, 4, at this point, mathematically, excuse my language, stuff hit the fan. Okay, it does. And it gets really, really complicated to the point where we have to do, well, grade 12 math if it ever gets to a point where you're using 4 terms. And so we simply call it a polynomial. Anything more than 3, we don't care to specify how many terms there are. We have better things to do, so we just group it together as poly. Okay? Now, as we look towards the lower part of this, I am going to introduce to you, I don't have actual algebra tiles for you to play with today, or, well, I don't have initially had it planned because of COVID reasons, where, you know, I don't want people to share, get close, and do things together too quickly. Long story short, I need you to think about these black and white or solid and hollow geometrical shapes as algebra tiles. So these filled in shapes, it represents 1. So the algebra tiles, can you call it the area, are going to be representing the values we're looking for. For example, a small square is going to be 1 by 1. So 1 times 1 is going to be 1. For this one, this length is exactly the same as the one above, but this longer length, I'm going to say, is some value x. So what is x times 1? X. So this long shape is going to represent x. Next, what if this length was x and the width here was also x? What is x times x? X squared. That's why it represents x squared. Okay. For now, please bear with me. I'm trying to use these visual shapes to help you add and subtract and group terms together. And so I'm just trying to get you prepared for the questions that are to come. If you see a shape that is hollow, let's pretend it represents -1. So the area is still 1, but I'm taking away that 1. This area is still x by 1, so it's x, but I'm trying to take away that x, and this is x times x. This is still x squared, but I'm taking away that x squared. So it's a negative, positive versus negative. Everyone's okay with that for now? Right, let's just, it's like a system, it's like a matching game. Let's move on to the next page. So all the solid blocks are going to be considered positives. Can you take these and group what I call like terms together, like tiles together? So let me write this down. I wonder if you can read this. Ready? This is x squared. That represents 1. This represents x squared. This is just x. This is what? 2, right? 1 and 1. So it's going to represent 2. The longer one is still x. These are 2 cubes together. That's 1 and 1. That's going to represent 2. And that's also an x. Let me see if I could write this normally. So that'd be x plus a 1 plus an x squared plus x plus 2 plus x plus 2 plus x. What does that equal? before you jump the gun saying, oh, what if I do x squared plus, like, does that mean it's x cubed? Before you get there, and that's not the answer, by the way, group or put together like tiles. This large square and that large square are the exact same. So how many large squares do I have? 1, 2. I have 2 of them. You see why I'm not adding it with just regular x's? They're different shapes. Next, I'll use green. How many? Let's do the rectangles. How many rectangles do I have? Yeah, I have 1 here. I have 1 here. I have 1 here. And so that is 3x. And lastly, I'll use red. Here's a regular square, a small square, and a small square. Together, I have 5. Congratulations, you have written an algebraic expression where I do not know what that number actually is. But if you know x, you can figure out what that statement is. If x was a 1, you can solve it. If x was a 2, you can solve it, so on and so forth. As some of you are savvy enough to know, oh, I see where this is going. There will be questions in the future where they give me the x and tell me to solve the entire thing. There will be questions like that, of course. Let's try some of the examples. Okay. Could you try, and remember, these hollow ones are negatives. Could you turn these shapes into terms and then group the like tiles together? In other words, group the like terms together. See what you can do. I'll give you about a minute. Okay. Turn those shapes into algebraic expressions. And I'll do the first one for you as a reminder. That big cube is x squared. That big cube is x squared. A hollow rectangle is an x, subtraction, of course. The hollow rectangle is an x, subtraction. And the tiny square is a 1. What is the algebraic expression for this? 30 seconds. Try it out. And I might as well do the same for these. This is an x. That's an x. That's an x, and that's an x squared. So, you know, this is actually a 2. That's like, there's 2 squares there. That's a 1 and a 1, and that's a 1. Okay. I'll give you a minute. Can you create algebraic expressions for both? Okay, so clearing this. Like people are working pretty hard. The final result would be, so that would be x squared, subtraction of x, and a subtraction of 1. So this would be, you're adding 2 x squareds, I'm subtracting 2 x's, and then I'm subtracting by a 1. Oh, okay, once again. I have an x squared. I'm adding it with another x. This means I'm subtracting a single x, and then I subtract another single x before subtracting a 2. So how many x squareds am I adding together? It's like that. Right? So this literally says 2 of x squareds. And here I'm subtracting an x twice. It's like saying I'm subtracting 2 of the x's. So -1 with another -1, you're adding it together. You can think about it like that. It's like integers. So this is why integers were so important for you to master. That's it. And this one, I'll do this very quickly. This is a negative, negative, negative. That's a negative. This is equal to, you know what? I'll just do it properly. That is a -x minus an x. Once again, I made the mistake. This is 2/2. That's a +2. Minus x plus 1 minus x squared. That will simplify into -x squared minus 3, I'm subtracting 3 times, plus 3, I'm adding 3 times. That's good. If you did not get these answers, just make a little note of where you made the error and remind yourself in the future. Yes. It does not, but by convention, later on, I will tell you that the higher degree is almost always put first. It just helps organize mathematicians' eyes so much that we consider it like a unwritten rule. Okay, so have the higher degree first. Now, here's what we don't call them like tiles, because what mathematicians have you seen using these tiles to do math? Never. But the reason why I introduced like tiles is because we can call them instead like terms. They are alike, and you can group them together because they have the same variable and the exponent. If they have the same variable and the exponent, we can consider them to be together and add them or subtract them, whichever works. Let's do a different color. Right? Same with this one, negative x, and negative x. They are all the same or like terms. And here I have a 2 with a 1 because there's no variables. And that negative x squared is by itself. Okay. Quick recap. Again, what is a term? What's a variable? What's a monomial, binomial, trinomial? And then, of course, what's a like term? There we go. Let's see if you can identify what the like terms are. I think if you think about it hard enough, A, you'll be okay with. B, you'll be okay with. But C starts to get a little funky. So I'm going to give you a minute. Would you please identify which like terms or which terms are like terms? I'll start with this. 2 has no variable. The 4 has no variable. They are like terms. How about I do this? Some of you might not have highlighters, so 2 and 4 are alike. Next. 2x, 3x, and 6x are like terms. You are only looking at the variable and the degree. You don't have to worry about the coefficient. The coefficient simply tells you how many x's or xy's or whatever you have. Just check to see what the like terms are, and then you can add them. Here? For this one, right. 2x cubed. This part? Going up here? Okay, no, these are the like terms. So this one, and these, this one, and that one, those 3 are all like terms. Okay. Well, next one. All right, let's start. U squared. Are there any other u squareds by themselves? Right there. So that and that are like terms. UV, just U and V, not square, no nothing, just UV, 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 none. U squared V, U squared V, U squared V. Those 2 are like terms. And U all alone, well, there's nothing else like that. Which brings me to the next one. Let's do the ones you know, and I'll save the unusual one for last. XZ. Are there any other XZs? There is. Are there any other XYs? There are. Huh. Are there any other numbers with no variables? No. And numbers with x squared z? No. So what to do with these two last terms? Please remember, whether I have 1 times 2 or 2 times 1, the result is the same. Therefore, x times y or y times x are the same. In other words, do you see the zx? Zx is the same as 2xz. This is the same as the other two. And 3yx is the same as 3xy. So this is the same as the other ones that are circled. In other words, don't think it's different. Don't think too deeply about it. They are the same. And you can group like terms together. You could even rearrange it to suit your needs. Yeah. One last tip, and this is everything else after the next page is essentially homework that I think you can try on your own. We'll do some hard ones together, of course. But one last tip I can give you before we try some questions and wrestle with it together is this thing called a zero pair. And to be honest, I did not know it was called a zero pair. I just did adding and subtracting. But for whatever reasons, they believe that we should label it. So let's do it. You know that this is considered a 1, and that's considered a negative 1. So what is 1 added to a negative 1? It'll be a 0. So a solid square and a blank square, they are 0 pairs because they make a 0. Here's an x, here's a negative x. So what is x added to a negative x? It would be 0x. And if it's 0 times x, we need the x. No, 0 times anything is just 0. So I don't know. I wrote it anyways just to show you. There's another one. This one is a single x squared. I'm being added to a single negative x squared. And so that's again, 0x squared, which is a 0. Okay. That's it. The entire day's exercise is to be able to group like terms. And of course, there's some extra things we can do. Let's do the like tiles. We'll do one example on the bottom of the page. And then I'm going to do one example with you of geometry. And then we'll call it a day where you can do the rest as homework. All right. Algebra tiles. That is x squared. That's added to an x. And please forgive me for the formatting. That was wrong of me. Okay. This is plus 2. This is subtracting x squared. This is adding an x. This is subtracting 2. This is adding a 1. This is adding an x. That's subtracting a 2x squared. And that's adding a 1. Group like terms. I have an x squared here, an x squared here, and an x squared here. I have a 1x here, a 1x here, a 1x there, and I have green, a 2, a -2, a +1, and a +1. Group-like terms. I'll give you a minute. Right now, you may still approach this as a matching of shapes. But as you do more and more of these, I do hope that you'll be able to see them with just numbers. So here's what I would do, for example, equals, of course, mathematical conventions. I have a +1, x squared. I have a +1, right? And I have a -1. Using that idea of 0 pairs, I know that this and that is going to turn into nothing. All that's left for the blue is -x squared. Next, +1, +1, +1. And so that doesn't cancel out. That's going to be a +3, 1 + 1 + 1. +2 and a -2, those will turn into nothing, leaving me with just +2. That's it. So it takes a little bit of careful watching of the eyes, but once you get that, everything else is just sort of putting things together. So of course, as I said just now, the next goal is to see if you can do it without algebra tiles. You can picture it in your head, of course, but if you can do it without, that's where we want to be. Moving to the next one, and I'll show you why not using algebra tiles is awesome afterwards. I have x and -x. I have 3 and a -5. Those are both like terms. The next question, I have an x squared here and an x squared here. They will group together. I have a 3x and a 2x that's going to group together. One -4 -3 or -3. 3 -5 -2. 2 -4 -2x squared. 3 + 2. This kind of language, this kind of skill is going to be everywhere for the remainder of your grade or for your high school math career. This algebra is your bread and butter. Super important. So keep on working on grouping like terms together. First visually, using the tiles in your head, and the next without, thus represented by the variables. Now, why would this, why, right? Why? Okay. I can't tell you the entire picture of the mathematical world, but I'm going to try to introduce your first set of unknowns, okay? Take a look. I'm going to go to the last page that has a square, funky looking ramp, like a reverse letter L and another reverse letter L. Go all the way to the last page where it looks like this. The question says, can you give me an expression, in other words, a mathematical statement for the perimeter? Anyone remember what the perimeter is for a rectangle? Yes, Sally? Yep. So if you had to walk all along the outside, what would that length be? Up until now, you were given numbers. But what if you're not given numbers? Let's start here. If I walk all the way to the left bottom corner, I walked a distance of 3x plus 5. And then I walked up. That means I added to my distance 2x plus 3. And then from here, I walked all the way to the right, which means I went the same distance as that bottom length. I added 3x plus 5 to my walking steps. And lastly, I came back to where I started, adding another 2x plus 3 to my steps. That is correct, but it doesn't look nice. It could be simplified. It could be made easier. It could be more digestible. How? Well, remember, these brackets, they're not multiplying. It doesn't serve a purpose. You don't have to write this, but this literally means 3x plus 5 plus 2x plus 3 plus 3x plus 5 plus 2x plus 3. Those brackets don't serve a purpose. There's no multiplication involved. So let's group the like terms. No algebra tiles. I'm not even going to color. I'm just going to do this as if I'm doing it with you as a student. 3x is here, 2x is there, 3x is here, 2x is there. Look at only the underlined word, underlined terms. 3, 2, 3, 2. 10x, good. Next, to help my eyes, there's a 5, 3, a 5, and a 3. I'm only going to focus on the circles. 5, 3, 5, 3. Good. Done. And I hope you're with me when I say, would you rather look at this or would you rather look at that? Right? This is why we're grouping like terms. It makes it a lot easier to look at, a lot nicer, to be more digestible, so on and so forth. Okay. I believe I made a bit of a mistake and not put any x values in here, but that's okay. You can sort of practice doing this without any x's. Okay. For example, I'll do this one with you very quickly. The perimeter, again, is the walk around. I don't have this distance, but I do see this symbol that tells me that any other length that has this single dash through it means it's the same length. That is a length of 5 inches. And so perimeter is, let's start here, 5 plus 7 plus 6 plus 5 plus 10 plus 15. Add that up. Question? And for example, like letter C, you'd have to use some logical problem solving to see if you can find it. So again, that's a 5. And to answer Damien's question, I am going to take a look at letter C. Take a look. Perimeter means I have to add all the distances around. So if I start here, that's 25, 5, 19, 13, and 18. There are no dashes, so you can't just copy and paste a number. However, what I do know is, assuming that this is all 90 degrees and it's all just like box corners, 19 plus this invisible distance is equal to 25. So there's my logic. This portion right here must be the full distance of 25 subtract this distance of 19. Another way you can do it is 25 minus 19 is a question mark. 19 plus the question mark gives me a full length of 25. I could write it that way as well. So being a mathematician, instead of using a question mark, how about we use the letter X? How do we find the letter X? You could guess and check, but instead I'm going to use algebra to find out what that X is by subtracting both sides by 19. 19 minus 19, I'm creating a zero pair. X is the same as 25 minus 19, which is a 6. Rejoice, everyone. This was a very long introduction because it had to cover all the foundational skills. However, please don't underestimate it because you think it's fairly simple. Please practice every example we have in this sheet. I will, as always, create an answer key and put it up online for you. This video will also go up. I hope that you can complete all this on your own time. If there's too many things to do today, do every other question. You know me. I want to ensure that you are doing a little bit every day and not just leaving it till the next class. Okay? Any questions about this lesson? All right. With what we covered today, please practice from the sheet. And yeah, that's it.